All right, so before we get into building the model of what this molecule actually looks like, let's take a look at how it looks structurally. The molecule in question is 3,4-dihydro-2H-pyran, which is a long name for a molecule that actually looks like this in a simple basic line diagram. The CAS number is 110-87-2, and this is the molecular formula, C5H8O. It has a molecular weight of 84.12 grams per mole, a melting point of -70 degrees Celsius, and a boiling point of 86 degrees Celsius, meaning that at 25 degrees, or room temperature, this molecule will be a liquid. Now, aside from all these physical properties, let's take a look at the structural properties. Here is a more advanced version of what that structure actually looks like, identifying the hydrogens along the edges, the oxygen bond, and the alkene right here. Now, if we take a look at the bond analysis, we get our accounts of the type of bonds that there are. There's one pi bond located here on the alkene functional group, and there's 14 sigma bonds around the structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Now, these is really important whenever you're considering the hybridization of the carbon molecules. Since there's 5 carbons total, you can take a look at them on a one-by-one basis, and it's actually reasonable to do so as opposed to a larger molecule. So the carbons that are not connected to the alkene, this one, and this one, are going to be sp3 hybridized because they're CH2 groups and because they aren't part of that double bonded system. These two molecules right here that are part of the alkene system are going to be sp2 hybridized, and they're effectively CH groups. Now, with this in mind, we can take a look at what constructing this molecule will actually look like with the Snatom set. Now, when constructing this molecule, it seems better to start from the base up, as you can see back here. We'll start with this oxygen atom, add a carbon onto this side, and a carbon onto this side. For one of the sides, we're going to have a double bond, meaning you have to add the two double bond signs to create your double bond to the carbon atom here. That snaps into place. You add your 4th carbon atom there, and then your 5th one to connect them together. And should snap into place, if I can get them to. Yeah, there you go. So the molecular geometry is rather three-dimensional rather than it just being planar. And when we go to add the hydrogens, you'll see how the hybridization of these molecules comes into play and what type of groups they are. This is the alkane functional group, meaning these carbons right here can only have one hydrogen bonded to them. These are not part of the alkene system, so you can add 2 hydrogens to them. You can do the same for everything, or every single other carbon that isn't part of the alkene system. And the reason we don't add any hydrogens onto our oxygen is because our oxygen has the lone pairs, so it doesn't want to have any extra hydrogens attached to it. Now, for the functional group analysis of this, as we've already stated, this is an alkene. It's got the double bond between 2 carbons. But what's also interesting about this molecule is that it has the ether functional group down here, which is a carbon connected to an oxygen connected back to another carbon. We can also get some insight into how the structure functions by deconstructing it. We can see that it takes relatively little effort to take these off compared to taking the larger molecules off, and compared to taking these apart because they have that added reinforced double bond here. There's nothing special going on with the oxygen other than the fact that there's an oxygen involved, so it's relatively easy to pull off. And these, because they're simple, regular carbons with just 2 hydrogens attached to them and they're not part of any larger functional group, then they're pretty simple to take apart too. So, with all that in mind, I hope that helps to elucidate the structure of 3,4-dihydro-2H-pyran.